In lots of previous videos, we've looked at how to calculate various permutations of the between groups analysis of variance. As we've covered in previous videos, that's a technique to compare several groups in terms of their scores on a single continuous dependent variable and see if there's a significant difference between the means. In the last video, we looked at the two-way between groups analysis of variance, and that's when we have two independent variables. In that case, we have a unique situation because we can not only look at the two effects of the independent variables on their own, but we can also look at the interaction between those effects. I used an example in the previous video that if we had two memory techniques, we could compare the effects of various memory techniques on the ability to learn a later word list, but we could also give one group easy words and one group difficult words and see if there's an interaction such that there's something unique about the combination of those factors. So maybe it's that one technique is good for easy words and the other technique is good for difficult words. In that video we looked at two independent variables, and I said that that's a much easier way to look at it, but that this approach generalizes to however many independent variables you wanted to look at. You could look at 50 if you wanted. In this video, I'm going to do the follow-up that I promised, and we're going to show how to look at it with more than two independent variables. I'm just going to do 3 because once you've done 3 or more, exactly the same procedures generalize it up to a 50-way analysis. So we're just going to focus on 3, and as you'll see, calculating even a 3-way ANOVA is incredibly cumbersome, and because, as we'll see later, later calculations require earlier ones. If you have any sort of rounding error, by the time you finish the analysis, you'll have rounded so many times that you'll only have an approximation of what your effects are. But I want to show this conceptually because a lot of people stop at show how to manually calculate a 2-way ANOVA and then stop there and don't go on to 3-way ANOVA, but it is very possible. So let's dive in. We've got our data here, and you see we've got 3 independent variables and then a score variable. The idea of this fictitious study was that we're going to give people a happy or a sad message and see how it affects their mood. But we also want to include more variables in that. So we had one variable that's the effort they were asked to put in, and another variable that's their gender, and we want to see if these variables produce a unique effect on their own, and if they all interact to produce a unique combination of effects. So if we kind of split that table, we can see we've got each of our variables has 2 levels. 2 times 2 times 2 is 8, so we've got 8 different groups, and first thing we need to do is calculate the means of our 8 groups, because that's going to be important in a second. We also need to calculate the grand mean, which is just the mean of all those means. We've seen in previous videos that in an ANOVA the variability in our study is explained by several different factors. It's explained by main effects, which is the effect of one unique variable on its own, disregarding any of the other variables and any of the other interactions. So in this case, because we've got 3 variables, we've got 3 main effects: the effect of emotion on its own, the effect of effort on its own, and the effect of gender on its own. We've also got two-way interactions with all those variables. So if we disregard the effect of gender, is there something unique about the combination of emotion and effort? And if we disregard the effect of effort, is there something unique about the combination of emotion and gender? And likewise, if we disregard emotion, is there's something unique about the effect of effort and gender. So, and then we also obviously have the highest order interaction. Some people consider this the most important interaction of between all our variables, emotion, effort and gender. Those two-way interactions, or whatever you've got one less variable between, are sometimes called marginal interactions because they're qualified by the highest order interaction. For example, we might know that we've got an interaction between emotion and effort, but if the three-way interaction is significant, we know that that's confounded or is different depending on what gender you are. So we want to interpret the highest order interaction, but to get there, we have to kind of sequentially work out all these effects first. So with that said, what's the process we're going to follow? Well, the process is very similar to what we've done in the past. First of all, we're going to calculate the total variability that there is in our study. Then we're going to calculate the variability due to error, because we've seen in previous ANOVA videos that there's only really two values in an ANOVA. There's the amount of variability we can explain by our study, and the amount that's due to things we can't explain. And the idea is that if we can explain more than we can't explain, then we're likely to get a significant effect. So the next 2 points are once we've calculated the total, we can calculate the variability due to error and the variability due to all our effects. Because of the way we calculate this, we have to do it separately for every marginal interaction. We saw in the two-way ANOVA video that what we do to calculate an interaction is if we have two variables, we can calculate the main effects of both those variables independently, and then calculate the total variability explained by our study, and then there are no other effects there. So whatever's explained by our study but not explained by either of the main effects must be due to our interaction. Well, in a three-way ANOVA, or any more than a two-way ANOVA, we can't just say calculate our main effects and then say anything that's left over is explained by our three-way interaction, because we have so many more things that could be explaining variability. So what we need to do is calculate each of our two-way interactions as well. But in order to do that, so we can just subtract our main effect from the total, we need to calculate the total separately for all of our marginal effects as well. And then once we know what all our marginal effects are and what our main effects are, we can take that all the way from the total to work out the highest order interaction. So it's quite complicated, but we'll get through it. So in order to calculate our error, we've been through this before, so I'm not going to dwell on it, but here are all our scores, and we're going to take the deviation between the raw score and the grand mean, because if there was no difference in our study, we wouldn't expect there to be any deviation from the grand mean, because all the scores would be the same. So all the variation in study is explained by the difference between the score and the grand mean. So in this case it's 2.83. We saw in previous videos that that gives us some negative numbers, as we see, so we need to square those values to get rid of the negative numbers so they don't cancel each other out. Once we've applied that to all our values, we can just add all those numbers up, and we get 698.662. That's the total variability to be explained in our study. Now we can calculate the total variability due to error. And if you think about this conceptually, if we're saying that the only thing that affected our participants was our manipulation, then everyone who's been assigned to a given group should have the same score, because they had the same thing done to them. So any difference between an individual score and the mean for that group is essentially error that we can't explain. To apply that principle, I'm just going to take the first group. So we're going to take the first score minus the mean and work out that deviation, and then we're going to square those deviations again to get rid of any negative numbers. So we see a squared deviation, and unsurprisingly we're then going to add all those numbers up to get a total measure of the error in that group. Then to I've done that for all our groups, so we're just going to add up the total, which is 26.65. So that's the total error variability in our study. So we've done the two easiest ones. Now we need to calculate the variability due to all our effects, but also we're going to do it separately for each of our interactions. So we're going to go back to this slide to get a good sense of what we're doing, because it's very easy to get lost in it. So first of all, we need to do all of our main effects. They're probably the simplest to do. So first, if we look at the main effect of emotion, if you remember from previous videos, what a main effect is saying is forgetting about all the other effects. If we just lump together all the happy people and all the sad people in this case, is there a difference between those groups when we forget about the other effects in our study? So we've just got, again, the means for each of these groups calculated regardless of how much effort they put in or what gender they were. So to calculate that effect, we need to do a very similar thing to what we did before. To take the group mean, so that's the group mean for all the happy people, which was 2.83, minus the grand mean, square that and multiply it by the group size. Now, because we have 24 people in our study and we have two groups and we're just lumping them together, you get 12 people in each group, so we do it plus multiply by 12 here. That's going to change as we get further in, because as we add in more and more of the interactions, our groups are going to get smaller and smaller because we're separating them depending on our variables. We're not just lumping them together. But for these main effects, they all involve two big groups, so it's going to be 12. Similarly, for the effect of effort, we take the mean for high effort and the mean for low effort, and substitute them into our equation. That accounted for 49.54 units of variability. And again, for the main effect of gender, we take our two means, 2.92 and the 8.25, and substitute them into our equation, 170.545 units of variability. We can now move on to our interactions, and we're still going to be using the same logic. We're still lumping groups together, because we're going to, unlike for the three-way interaction, if we're just looking at the interaction of emotion and effort, we are going to separate out the different groups for emotion and effort, but we're going to forget about gender. So if we just see what that looks like, conceptually we need to be aware again that an interaction equals the total model minus all of our main effects that we've already calculated, because we know they're explained by the main effects, not the interaction. So to calculate the full model, what we need to do is lump our scores into just those two factors that are explained by the interaction, and forget about the gender for now. So if we substitute those values into the equation that we used before, so again, for each group, that's the group mean minus the grand mean squared times the number of people. And like I said, because we're getting a bit more specific now, involving one more variable, the groups are half the size, because we're not just lumping them together. we're actually separating them out a bit, and you'll see when we do the effect of gender, because those groups are even more specific, the group size declines even more. So anyway, we know that the total variability explained by emotion and effort and their interaction is 268.66 units. So to calculate our emotion by effort interaction, we can take that amount, 268.66, and take away the main effect of emotion and the main effect of effort, and we're left with 33.84 units. Likewise for the effect of emotion and gender, this time we're going to forget about the effort someone's put in, and just lump together the different efforts and only separate out between based on emotion and gender. So and calculate the means overall just based on those groups. If we look at our equation again, we see the same equation. We take each group mean minus the grand mean squared times the number of groups. So we see that total variability explained by all our effects of emotion and gender is 494.59. Again, to calculate the interaction, we can just take that total minus the relevant main effects and be left with the interaction term. So the main effect of emotion was 181.28. Also taking out the effect of gender, which was 170.45, we're left with 142.86. For our last marginal interaction, this is probably getting a little laborious now, even just watching it. We're going to forget about the main effect of, or forget about the effect of emotion, and just lump together high and low effort people with males and females, regardless of how much, regardless of what emotion is on. So again, we're going to take the means of those groups, and again we're going to do the mean minus the grand mean squared times by the group size, and yet again we see that our group size is 6 because we're getting a bit more specific than we did when we're just lumping together for the main effects, but we're not including the variability of the third factor yet. We're just looking at two-way interactions, and for that our total amount of variability is 293.15. We can then use the same logic to take away the relevant main effects from that, so the effect of effort and the effect of gender, and be left with 73.16. We can now calculate our three-way interactions. We know that if we know the total amount of variability explained in our study and take away all the effects we've already calculated, we know that the only effect that's left is the three-way interaction. So if we look at that kind of in an equation form, we know that the highest order interaction equals the full model, the full amount of variability we can explain, minus or all the marginal effects, or all the effects that don't include all variables. And to calculate what our model is, we can just because we know that the total is made up of all our effects plus error, we can just take the total which we calculated earlier and subtract the error which we calculated earlier. So we know that the total amount of variability we can explain is 672.03 units. Well, going by the logic we saw earlier, we should be able to subtract all the effects we've calculated from that value to be left with the amount of variability explained by our highest order interaction, which is 16.9 units. So now we've got the amount of variance explained by each of our units. We need to create an average or average amount of variability explained by each effect. That's called a mean square. Before we can do that, we need to work out, rather like you calculating any average in anything, we need to work out how many entities contributed to that effect, to work out what to divide by. That's called degrees of freedom, and we've seen degrees of freedom for lots of statistical tests, and degrees of freedom generally equals the scores involved minus the scores that aren't free to change. So the example I always use for this is if you have balls in a bag that are different colours, the last ball that you pick, you don't have a choice because there's only one there. So generically, degrees of freedom equals scores involved minus fixed scores, and our degrees of freedom for our error, so average error variance, equals the total number of participants we had minus the total number of group means, which we saw was 8, so got 16 degrees of freedom for error. From main effects, our degrees of freedom is simply the number of means being compared minus 1. So remember, the main effect is just the effect of one independent variable while forgetting about all the other effects. So each of our independent variables have two groups, so we can see that the 2 minus 1 equals 1. The degrees of freedom for an interaction are simply the product of the degrees of freedom for all relevant main effects. So in this case, we see we for the emotion by effort interaction, we saw earlier that emotion had 1 degree of freedom and effort has 1 degree of freedom, so 1 times 1 equals 1. Likewise for the three-way interaction, even, emotion has 1 degree of freedom, effort has 1 degree of freedom, and gender has 1 degree of freedom, so 1 times 1 times 1 equals 1. Where this would be different, for example, is because if we had three groups in emotion, so we had happy, sad, and neutral, and 2 for effort, it would be 2 for gender, it would be 2 times 1 times 1. And then obviously we have 2 degrees of freedom. So once we've calculated that for all our effects, we can calculate the mean square. This is the average I was talking about. Generally, the mean square equals the total sum of variability in our study divided by the degrees of freedom, that number of entities we just talked about. So our mean square for emotion equals 181.28, that value we just calculated for our main effect, divided by its degrees of freedom, which we just saw was 1, which equals 181.28. For our main effect of error, just to show you, hopefully you've caught this already, but earlier on we calculated that our error was 26.65 and the 8 means contributed to it, so it had 16 degrees of freedom. The reason why that's important to calculate separately is F statistic, which is what we're going to work out a probability value based on, is computed as the mean square for the effect we're interested in, always divided or corrected for that error mean square. So if we put that into use here, we see that the main effect for emotion equals the mean square for that effect divided by the error, which equals 108.55 in this case, just to show that exactly the same logic applies for however high interactions you want to get. We take the sum of squares for our three-way interaction divided by that error estimate, and we get 10.12. So we've now we've now calculated all our effects and using our means our f values and our degrees of freedom, we can calculate the probability values for all our effects. It's worth noting that if you're going to put this into a p-value calculator, it'll ask you for degrees of freedom 1 and degrees of freedom 2. Degrees of freedom 1 is the first thing you use to calculate that f value, so remember we took the sum of squares, and degrees of freedom 2 is the second thing we use to calculate the f value, which remember we always took the error. So in this case it'd be use the respective degrees of freedom. So for all our effects we test them against 1 and 16, and we find that all our main effects are highly significant, as are all our two-way interactions, and most importantly, as we saw, because if this interaction is significant, then that means our other interactions are superseded by this interaction. We see that the three-way interaction is indeed significant. So that was how to do a three-way ANOVA by hand. This generalizes to however many variables you want to use. If we had a four-way ANOVA, we would calculate the main effects, calculate the two-way interactions, and then we would calculate the three-way interactions and subtract all that from the total variability to be left with our four-way interaction. So the higher up you go, the more effects you have, the more complicated it becomes, and the more confusing they are to interpret. So one thing I want to kind of emphasize about hand calculation is if you did put these data into a statistics program and calculate it as a three-way ANOVA, you would get different slightly different results, because rounding number rounding is an issue, because pretty much all of your calculations involve things you've calculated previously. There's a lot of opportunity for human error just to kind of confound and snowball, because if you get one thing wrong, you're going to put the wrong thing into the next calculation. So I wanted to show you that it's not conceptually it's not difficult to work out how to work out an ANOVA with as many variables as you want, and I don't know why more books don't go into it, but in terms of actually doing it and multi-factor ANOVA, I wouldn't actually do this. I would just calculate it on a computer at that point. Two-way I think is okay, but three-way just gets so confusing, and certainly anything more than that would just be hellishly confusing. But I wanted to show you again that conceptually it's not that difficult. So anyway, guys, thank you for watching this video. I hope you've enjoyed it. Bye bye.